Hey guys, so in this video I would like to discuss an interesting concept. I have touched upon various aspects of this same concept in one or two of my previous videos, but in this video I want to discuss the same or similar things but in a slightly different perspective, and I should say a slightly better perspective. So we know something called Helmholtz free energy, which is often referred to as simply the free energy of a system, which is U minus Ts, where U is the internal energy of the system and T is the temperature at which the system is kept, and S is the entropy of the system, entropy of the state of the system. I mean, we measure the entropy at one particular point. So if the system is at some particular state at that point, then S is the entropy of that state. Okay. So of course I'll not be delving deep into technical statistical mechanics terms and concepts like macrostates, microstates, and all these things. But this will, I think, I'll try to keep the discussion for layman, aimed at a layman audience. But this is very interesting, and like whenever we study the change of any system around us, very naively we can say that everything around us tries to reach an equilibrium state by losing energy. So there's a concept of energy minimization. And if you've studied a little bit of entropy, thermodynamics, second law of thermodynamics, you don't even need to go to statistical mechanics. Even from the second law of thermodynamics, we know that the entropy of everything must increase, right? Entropy of a closed system cannot decrease. That is the more technical term. Entropy, if it's an open system, if the system is interacting, exchanging information with its surroundings and all, then of course the entropy can, locally the entropy of a system can decrease provided the entropy of the surrounding increases, and as a whole the entropy of the system plus surroundings increases. But if it's a closed system, if it does not interact with the surroundings at all, then its entropy will either remain the same if it's at in perfect equilibrium, or it can increase, but it can never decrease. So from that, and you must have looked heard of some different analogies about entropy, like entropy disorder and these kind of things. And if you have thought about this, even without knowing statistical physics and everything in detail, I think it's obvious. Like you can say that everything around us, most of the changes that happen around us, you can understand that in terms of like everything is trying to maximize that entropy. So there are two different kind of optimizations that we see in nature around us. One is energy minimization and one is entropy maximization. Everything will try to minimize their energy and everything will try to maximize their entropy. This is a very qualitative description, and yeah, this is not incorrect, but this misses out on a lot of technical details which you must consider if you really want to understand everything, because there are a lot of phenomena around us which are very counterintuitive. It's not always a very simple phenomena that can be analyzed using this very simplistic idealistic viewpoint. So this free energy, the concept of free energy, this is a very important and fundamental parameter, because rather than saying everything tries to minimize energy or maximize entropy, it would be better if we say that everything tries to minimize its free energy, because we kind of take both into account when we say this. So now we will just discuss this point with a few examples. I'll not try to make the video very long, but before that we need to understand what is free energy. Just a very basic definition. So free energy is defined as, I will not go into how it was derived, I will not discuss thermodynamic potentials or anything, but just the definition. That is all we need to appreciate the perspective I want to share with you. Okay. So the free energy of a system is defined as, I told you, U minus Ts. U is its internal energy and S is its entropy. T is the temperature at which we are studying the system. So when we say energy minimization, a system will try to minimize its internal energy U. So F is the free energy. So F equals U minus Ts. So if U is minimized, then F is also minimized. I mean, if U decreases, F also decreases, because F is U minus Ts. On the other hand, if entropy S is maximized, then also the free energy F decreases, because F is U minus Ts. So in the entropy term Ts, there is a negative sign before the entropy term. So now does that mean both of these things are equivalent, like energy minimization is equal to or is equivalent to entropy maximization? Not exactly. They have the similar effect. Both of them have decreases the free energy, but it's not like both are equivalent or they decrease the free energy by the same amount. It depends on the system we are studying, especially the like see, if you talk about a system at a very high temperature, if the temperature becomes dominant, if the T becomes dominant, I'm talking about, then entropy maximization will play a more dominant role than energy minimization, because we have the entropy S multiplied by T, so U minus Ts. So the second term will dominate if we deal with the very high temperatures. In some cases, energy minimization will play a more dominant role. So they go hand in hand, but understanding which is more important in the context of the system we are studying is very important. to better analyze these physical systems. That is the main point I wanted to convey. And now I will illustrate this with a few examples before finishing this video. So the first example is when you heat a substance. For instance, if you heat a solid, let's say iron rod or something, steel rod or something, it expands on being heated, right? We expect, that's what we expect when we heat most objects. It expands if we heat it to sufficiently high temperatures. So why does it expand? Because, see, since we're talking about very high temperatures, the entropy maximization will play a more dominant role than energy minimization. And when we talk about entropy maximization, if it expands, if the iron rod, steel rod, or whatever the system, if it expands, then essentially more volume is available to its constituent atoms, molecules, or whatever, and they can more volume becomes available to them. They can move about more freely, and the number of possible configurations, the number of microstates increases. So basically, entropy is the number of ways you can arrange the particles within a system. If I put it very qualitatively, I don't want to go into discussions of microstates and macrostates and technical definition of entropy, but yeah, in general, if the volume increases, the volume available to the particles increases, the particles can move about more freely, and they can attain many possible configurations. Configuration is just the particles can move about and arrange themselves in many possible ways. So increasing the volume means increasing the entropy. That is why due to the entropy maximization, the substance expands on being heated. And since we're talking about on being heated, we're talking about high temperatures, so here entropy will play a dominant role, not the energy minimization. But I don't know if you've noticed, when we heat rubber bands, then it contracts on heating. It does not expand, which is contrary to what we might expect. But so why does this happen? Now again, the reason is same. When we heat something, be it a rubber band or be it a solid iron rod or whatever, entropy maximization will play a leading role, and here also it does. But so then you may ask, why does it contract and not expand? Because rubbers are made up of a special kind of substance called polymers, and that is the second example we'll be discussing, in fact, because it's all connected. And see, you can think of polymers. You don't need to go into the chemistry, biology of polymers. Even I don't understand any of that. But yeah, basically polymers are like chains. They are not free particles. They are just chains of molecules or something like that. The structure is like chain structure. Okay. So a rubber is a very like interconnected network of polymers, a lot of chains. So if a rubber expands, you just think of it. There are many chains like this in the rubber. So if you expand it, then the chains become perfectly stretched out. If you expand a string, it becomes stretched out. But if you do not expand it, or if you just let it, then it will maybe wiggle around like this. Now if you have many such strings, and if you expand the entire structure, the rubber band, then everything becomes stretched out and in a kind of orderly configuration, because the number of ways in which all the strings will be stretched out is much less than the number of ways in which the strings will be coiled around and in a disordered configuration. So when the rubber band contracts, actually all the polymers, they do not stretch, but they coil among themselves, and the disorder, the randomness, or the complexity of the system increases, and so does the entropy. So the rubber band contracts for the same reason. It wants to maximize entropy as well. But since it's a very different structurally, it's very different than iron rod or something, that it does not expand. The point I want to convey is that by studying entropy, by thinking of all these systems, all the changes around us in terms of free energy, entropy maximization, and energy minimization, you can explain a lot of apparently counterintuitive phenomena. If you don't know about entropy maximization and all these things, it might appear counterintuitive and strange. Like, why does something expand on heating but some other thing contracts on heating? And because, so I said about this polymers thing, but polymers are again a very interesting and very active area of research in physics, in all this active matter physics and study of biological systems, because polymers are a very important constituent of our cells and biology and our DNA and all. So it's of very very much of interest to not only to physicists but also to biologists. And yeah, most of the research is interdisciplinary, so there are applications in biology, but you need physics to analyze these systems. Now the point is, it's often observed that if you suppose you have two polymers, like two chain like structures, and if you keep them in a very confined fixed volume, very small volume, they are found to spontaneously separate. They move away from each other. So but in the case of rubber band, when we heat the rubber band, what do we observe? Like, the polymers become entangled and the rubber band contracts. Or even in general, if you take a box of gas where you have two different kinds of gas molecules, A and B, and you leave them as they are, then they will of course mix over time, like diffusion, right? Diffusion, and they will mix over time, because that is the configuration with both the minimum energy and the maximum entropy. When both gases are mixed, then the disorder, the number of configuration increases, because it's all over the place. Both the gas particles, both the types of gas particles, they're all over the place. Otherwise you have only gas A to the left of the box and gas B to the right of the box. There are very few ways you can achieve this configuration. Hence that's a low entropy state, and that's not favorable. The system will try to maximize entropy. So usually the diffusion occurs, and diffusion means also equilibrium. If there is only gas A on the left and gas B on the right, that's not equilibrium. But if they're all mixed together, it's in equilibrium. And energy minimization, because yeah, you can think of it like this. A closed system, like if it's a system of gas, a box of gas which does not interact with its surroundings, isolated box of gas. For a closed system, it will try to distribute energy uniformly throughout the system. So if both the all the gas molecules are mixed together in a diffused state, they are all randomly colliding with each other and all. So the energy is evenly spread out. It's uniform energy density. It's not like the energy is more here and less here. And if it's an open system, if it can interact and if it can exchange energy with its surroundings, then it will try to give up energy and minimize its own internal energy, right? So the point is, yeah, so we expect in general when we have A and B, when we have two different kinds of something, they will usually mix over time. That's what we apparently expect. That's what we observe in gas particles as well. But polymers, on the other hand, even if you keep the polymers mixed, they will automatically separate if they're kept within a fixed volume. See, when we're talking about heating a rubber band, there is no constraint on the volume. It's just a rubber band. It will contract. But if you keep the polymers in a fixed volume, this volume is fixed, very small confined space. It cannot go outside the volume. So if the polymers are mixed, entangled, and they like one lies over the other mixed, then this I don't know what it might appear at first glance, but actually this is a state of low entropy because the polymers cannot freely vibrate. I mean, there is one chain and another chain is sitting over it. So both cannot freely vibrate. The possible degrees of freedom, the number of ways they can vibrate, and hence the number of configuration decreases when they're mixed up, and that's why entropy is less here. So that's why to increase the entropy, they will automatically separate out. If we have one chain here and one chain here, this can vibrate freely, this can vibrate freely. They are not lying one over the other. So the guiding principle, the optimization principles are the same: energy minimization, entropy maximization, or overall, if you want to say it like this, free energy minimization. So sometimes polymers demix, sometimes the rubber bands are contracting, sometimes expanding. All of this might appear counterintuitive, right? So like how to understand what will happen, but the guiding principle is the same in all of the cases. All the systems, they try to maximize their entropy or minimize their energy. And this is the beauty of physics. Like there is so much complexity and apparently so much randomness in the world around us, right? But the beauty of a subject like physics and maybe even mathematics is that it can kind of, I don't know what to say, it can project, or it can find some parameters which, if you study these complex systems on the basis of this parameter, if you study the complex system on the basis of these parameters, then everything becomes very like simple and kind of universal. Like this thing I told you, entropy maximization, energy minimization, this is a universal. Like we don't expect any violation. Of course, the second law of thermodynamics is a statistical law. Of course, it's often said the entropy of a closed system cannot decrease, but there are a few, there is a little wiggle room here. If you go deep into the fundamental philosophy of statistical mechanics, like postulate of equal a priori probability, ergodic hypothesis, and so on and so forth, then there is something called past hypothesis. You cannot assert that over a long period of time a system does not automatically collapse to a low entropy state from a high entropy state. That can also happen, but yeah, those are all theoretical curiosity. In our day-to-day life, we don't expect any such behavior. So yeah, for practical purposes, to study real life systems, you can call this law of minimizing energy and maximizing entropy as a universal law. And that's the beauty, because just by using these optimization principles, you can study a wide range of phenomena which apparently look very different from one another. So yeah, that's what I wanted to discuss in this video. And yeah, I hope you like it, and please share if you have anything to say about this, any questions, or maybe if you have any suggestions or for me, or any other insight you would like to share about the subject, because yeah, I'm also not an expert. I might have, yeah, so you can always comment below. Thank you so much.